Welcome to the Center for Astrophysics Colloquium. My name is John Raymond from the Center for Astrophysics, and today's speaker is Mike Stevens, also from the Center for Astrophysics. Mike did his graduate work at MIT in the Space Plasma Physics group with John Belcher and Al Lazarus. He got involved with the Voyager Plasma Science experiment just at the exciting time that the Voyagers were crossing the termination shock and beginning to leave the solar system. He wrote his PhD thesis on fast magnetic reconnection in interplanetary space. And after that, he joined the Center for Integrated Space Weather Modeling at Boston University, where he worked on developing and testing physics-based space weather forecasting models. While he was there, he started to collaborate with Justin Kasper's team at SAO to propose Voyager-like plasma instruments for the Solar Orbiter and Solar Probe Plus missions. When the Solar Probe proposal was successful, he came over to SAO as a postdoc and joined the high energy staff shortly after that. In the long lead up to what is now the Parker Solar Probe mission, Mike was part of the team that refurbished and launched the Discover Faraday Cup experiment. That was an instrument that had been built at MIT for the canceled Triana climate science mission and was later reborn as a space weather monitor for NOAA. His work with Discover was recognized by NASA with a citation for outstanding contributions to mission success. Mike also took a leadership role with the Wind mission, where he's been acting in lead for the Solar Wind Experiment Faraday Cup and PI on a number of associated proposals. Mike is a co-investigator with similar experiments on two upcoming missions, the Europa Clipper and Helioswarm. And he's a co-investigator on the SWEEP experiment for Parker Solar Probe, in charge of data analysis for the Solar Probe Cup. In 2019, he accepted the NASA Silver Achievement Medal on behalf of the SWEEP team. So today, Mike is going to tell us about how Parker Solar Probe became entangled in magnetic switchbacks on the way to the solar corona. Mike.
Thanks, John. Thank you very, very much for the invitation. I always imagined giving the CFA Colloquium someday. I didn't really imagine it like this. I thought I'd have pants on. Just kidding, I've got pants on. But I hope that I am more entertaining than your email or your podcasts or whatever else you got going on in the background. Because I am excited to tell you about this. The Parker Solar Probe mission is pretty spectacular, and it's got some really fun stories. And it's a treat for me to be able to tell you about that, and also to be able to talk about the work that so many of my co-authors have been doing. I'm not going to be able to take credit for more than a small fraction of what I'm about to tell you about. This is the Parker Solar Probe SWEEP team that's at SAO. So SWEEP stands for the Solar Wind Electrons, Alphas, and Protons experiment. And the part of the sensor that we built at SAO is called the Solar Probe Cup. I'll explain it a little bit. Justin Kasper is the PI. He was here at SAO at the time. Now he works at BWXT, but he's still working on the experiment. Tony Case is the SPC instrument scientist here, so he's kind of our group leader. Kelly Korick was the head of ops. She's on detail at NASA headquarters, and we're looking forward to having her back at the end of that. And then also our postdocs, our SWEEP postdocs here at SAO are Christoph Paulsen, Tatiana Niembro-Hernandez, and Yemi Rivera. These are people who have contributed a great deal also in co-authorship to a lot of the studies that I'm going to cite here. So keep that in mind. These are big efforts involving a lot of people, so they have big author lists sometimes. But you're going to be hearing about things that they've contributed substantially to, indispensably to. And also our support scientists, Joy Velasquez and Lucas Gugliano, who help us run data processing here and operations. Oops. There we go. Okay, so here's what we're going to talk about today. Our first results paper came out after the first couple of Parker Solar Probe orbits. It was called Alphanic Velocity Spikes and Rotational Flows in Near-Sun Solar Wind, and it was in Nature in 2019. And it hit on two really big, interesting first observations. And one had to do with the co-rotation of the solar wind and the implications of that for solar spin down. And the second had to do with these magnetic switchbacks that I mentioned in the title. So what I thought would be good to do at this juncture, and it's particularly timely, and I'll explain why later, is to revisit those results with what we've learned since 2019. So the first thing we'll do is we'll do a little overview of the spacecraft. This is the fun story time part of the talk. I like to use this picture right here, despite all of the amazing visuals that the Pixar alumni at NASA Visualization Studios give us, because it shows a really, really important key thing, which is just that the part of the solar wind that we really understand well, the fast solar wind, it comes from coronal holes. So the sun's mouth there is showing you basically how it works. The first objective of Parker Solar Probe is to determine the structure and dynamics of magnetic fields at the sources of both the fast and the slow solar wind. And the part that we understand is the fast solar wind, and that's the part that comes from coronal holes like we're showing here. So the big question mainly for this part is, what is the slow solar wind? There are these two different states, and as you can gather, one is very fast and one is relatively very slow, but they have a lot of different properties. I'm not going to go into very specifically, but we're going to touch on. The second objective is to trace the flow of energy that heats the corona and accelerates the solar wind. And this is just another way of saying, do the coronal heating problem. You know, we know that the solar wind and the corona are about 1,000 times hotter than the sun itself. There's a lot of nuance to this problem. You know, we know it has to do with the conversion of magnetic energy in the corona, but this is not a problem that's been surrounded by any means in heliophysics. So it's still considered an open problem. So the place that we're actually going when we say that we're going to go to the sun in order to investigate these problems is beyond the solar Alphane point. And I'm sure many of you are familiar with the idea of the Alphane point, probably with respect to accretion disks and other stars and all sorts of other places where it's relevant. But here are the basic differences between being in the solar atmosphere below the Alphane point and being out in the free expanding solar wind. So one is that the solar wind is going to be co-rotating, bounced together with the sun below some height. And that's going to be because of the magnetic torque from the sun's magnetic field. Below the Alphane point, you have magnetic loops. You have plasmas that are confined, whereas outside, where Earth is, we see things that are mostly in an open topology, just mostly flowing out. Okay. Below, when you do have those magnetic loops, you have flows both ways. You have downflows and you have upflows, and you have intersections between the two, and you have interactions between the two. Whereas outside, we mostly have outflows. In those magnetic loops, you can have bidirectional MHD waves, and that's the way that you fertilize the ground, to have a whole rich spectrum of fluctuations that would be available to get sucked up by the plasma via all the different resonances that you can put energy into a plasma by. So bidirectional MHD waves is very important, and it's a really key difference, because out in the solar wind, you mostly only have outward directed waves. You have some that are heading upstream, but they're not actually getting back to the sun. There's a little bit that's heading upstream in the frame of reference of the plasma, but it's a very, very small fraction. And so you have the heating and the acceleration of the particles that's leaving their stamps on them below the Alphane point, whereas outside, what we're mostly studying when we're out in space with near Earth observatories is the cooling and the relaxation of the solar wind. The other thing that we're looking to see is segregated wind streams. So the fast and the slow solar wind stream states are going to be separated according to their sources when we get down below this point, when everything is confined or on open topologies. Whereas out in space, we have interacting gas and everything's pretty much mixed up. And then finally, eruptions, of course, below the Alphane point, that's where solar eruptions are still forming. That's where we're going to be able to study how they lift off. Whereas outside, we're just seeing them drift away from the sun. And below the Alphane point, that's the stuff that we study, so far. Those are the things that we've studied only with telescopes. That's stuff that's only been studied remotely. Whereas outside of the Alphane point, that's where we've sent space probes so far, a great many space probes. So this is our this is our mission to change that. This is our mission to actually go and send plasma diagnostics into that plasma environment where all of the action is happening in the corona. So where actually is the solar Alphane point? Here are two ways that we can pin it down that it's going to be around the like 5 our sun out to maybe 25, 30 our sun range. One way is from coronagraphs, and this result here on the side by Craig DeForest. It's showing you a way to measure the amount of downflow that you can see in coronagraphs. So what he does is, he'll take a ray along a radial cut along a coronagraph, and then you chart the brightness enhancements that you see in it from the sun over time, and you make height versus time plots, and you find the optical power there. You convert that to velocities, and you can sort out the part of it that's going outwards and the part of it that's going inward. And using this this technique that he's developed, it's a lot of image processing is what it sort of boils down to. You can see structured downflows going out to about 12 to 13 solar radii. So that's the largest loops that we can really see remotely. So the Alphane point would be somewhere just beyond where we see the outermost downflows. On the right, this is a representation of what we think of as the sort of information surface. And this is from a paper that Justin did with several of us at SAO. And this is portraying the Alphane surface as an information boundary. And so the way that this was derived was to look at the information that's stored in the phase-space distributions of plasma at 1 AU, and then model it as being de-excited by collisions and turbulence in order to round off the non-equilibrium features. And through the model that he developed, they pegged that the closest in that the non-equilibrium features in the solar wind VDF could survive would be in around 2030 solar radii. And they also figured that breathes in and out over the course of the solar cycle, which is an interesting result as well. So that's where we want to go. And the good news is that Parker Solar Probe is designed to go well below those distances to really penetrate that regime. This is an overview of Solar Probe, and you can see Solar Probe launched in 2018 in August. It's going to have 25 orbits in its nominal mission. Its first perihelion was in November of 2018, out here at a distance of 35.7 our sun. And where we're ultimately going to go is in below 10 our sun, and we'll get there Christmas Eve of 2024. In this picture, yellow is showing the orbits where we've been, and red is showing the orbits where we're going. And the way that we change the orbit, of course, is by doing gravitational assists at Venus. So there are 7 different places over the course of this mission lifetime where Parker Solar Probe has passed ahead of Venus and shed a little bit of angular momentum in the process in order to work its way down into this little cometary sort of orbit, except, well, cometary with a aphelion out near Venus and a perihelion that's inside of the Alphane point. And when we get there, that's going to put us roundabouts the scale where we're seeing, even remotely, where we see confined loops. In this picture, I'm showing a LASCO coronagraph. So this is from a vantage point just upstream of the Earth. And it's watching this solar storm happen. And this is Parker Solar Probe, not to scale, of course, but just about where it's going to be at perihelion. And from this, you can really see that it's going to be touching a lot of these loops as they're lifting off, and as you can still see the connection back to the sun. So now here's the most recent orbit that we've made. This is orbit 9, which would be just over this past summer. And this is going to bring you up to where we are presently. So our perihelion, our most recent perihelion was on August 24th there. And then right about now, I thought I set this to loop. Right about now, we're out here at our aphelion point, and we're getting close. If you see, you'll see Venus start to come around at the very end. We're getting close to this point over here where we're going to do a Venus encounter, and we're actually just about to do one of those orbital adjustments So our next orbit, orbit 10, is going to dive in just a little bit closer. I think Venus is going to come into view here at the very end. Oh, it didn't quite make it. You'll have to trust me on that. And this is what the Parker Solar Probe spacecraft looks like. There's a lot of interesting stuff that I could rhapsodize about with Parker Solar Probe. One of my favorite things about it is the solar panels you see here on the side. When it goes in for an encounter, of course, sunlight is abundant. So it does this neat maneuver where it actually folds its solar panels back and pins them against its body, and then just uses that outermost segment in order to power the spacecraft. But the instruments that are on board, first is ours. This is a suite of instruments for measuring plasma of particle detectors. And I'll show you what those look like in a minute. But there's also a magnetic field and electric field instrument. So they're measuring waves and they're measuring DC fields in space. There's also an energetic particle detector, which is a separate suite from the sweep plasma suite. They're a little bit of a sleeper right now. They're kind of hanging out waiting for solar maximum. Right now we're towards the end of solar minimum and then the beginning of the new cycle. So there hasn't been a heck of a lot that's happened. They're looking for eruptions and they're looking for big shocks and things like that that are going to cause radiation events in space. And they're getting antsy. They can't wait for something cool to happen, but so far not much. And then there's also a white light imager, and it's taking images a lot like the coronagraphs, like the one I just showed you, but it's taking pictures off the side of the spacecraft. And the idea with that experiment is that they're actually going to be able to image in white light the stuff before we fly through it. And when we make these perihelion dives, we'll be moving fast enough that we expect to be able to see certain streamers with the white light imager and then fly right through them and see them with the particle detectors. And right now there are a lot of people working on correlating what we've seen so far to see if that's happened yet. So here is looking up from behind Parker Solar Probe, and I chose this vantage point here so that you can see our instrument, which is the Solar Probe Cup. We are the one particle detector that peeks out from behind that gigantic heat shield that's protecting the rest of the spacecraft bus. So our instrument gets very, very hot, and there's some really genius thermal engineering that's gone into that from the engineering staff here at SAO to make this work. What our detector does is it measures the distributions mostly of protons and also of alpha particles in the solar wind. And it snapshots them very, very, very fast and continuously. And it's mostly working when the flux of the solar wind, is straight into the z-axis, that's the shield axis of the spacecraft when it's radial. Of course, Parker Solar Probe, making these diving orbits, is going to move sideways extremely, extremely fast. And we take advantage of that fact by putting these other two particle detectors along the side. So these are the Solar Probe analyzers, and these are much, much less sensitive to sunlight, or much, much more sensitive to sunlight. So they wouldn't be safe if they were out in front of the heat shield. We can't put them up front like we can put Solar Probe Cup, but when the spacecraft is flying sideways during a perihelion, it actually gets up to like 200 kilometers a second, which is comparable to the solar wind speed. And that's when the flow goes into these detectors, and they measure three-dimensional distributions. So this is a depiction of the proton velocity distribution from a recent orbit. And one interesting feature in this, of course, is you'll see that this is not in local thermodynamic equilibrium. This isn't a Gaussian distribution. It's got a little heat flux tail sticking out here. It's fatter in this direction than it is, it's fatter across the magnetic field than it is along the magnetic field. And that's the type of information that we've been trying to study at 1AU, but mostly gets erased on its way out to us at that distance. So now that you know a little bit about the spacecraft and about the suite, let's go back to those two first results that I mentioned, that first results paper. So the first one is about co-rotational velocity of the solar wind that we measured in the early orbits and the implications of that for solar spin down. And here's what our expectation was. Okay, we actually know pretty well, what the spin down of the sun should come out to be. It's a simple estimation that I learned, I think, when I was in grad school so that I could impress the committee giving my interrogation. You know the solar wind mass flux, and you say, okay, as this mass crosses the Alphane point, it's roughly co-rotating with the sun, so it's carrying a calculable amount of angular momentum. And then if you compare that to the actual angular momentum of the sun, you can get a timescale out of that. We have all of those elements. We don't know exactly where the Alphane point is, but I gave you a pretty good idea. It's around 10 to 20 our sun. We know the mass loss rate pretty well. We've flown all sorts of spacecraft into all sorts of places through the heliosphere to measure that over a long period of time from a lot of different vantage points. And of course, we know the rotation period of the sun. So we're all set. We can measure that. And the spin down timescale we figure is about 10 billion years. That's how long it would take for the sun to lose a sun's worth of angular momentum, if you will. So this is what we're expecting going into those early orbits. With orbits out here, we weren't expecting to get anywhere near the co-rotating regime. This would be in there around our 10, our sun. But of course, we do expect ultimately to get to the orbits where we will be seeing some co-rotational speed. So in orbits 1 and 2, when we're out here, then this is obviously a schematic, we weren't expecting anything measurable at all in the off-radial directions. So here's what we actually saw. And this was the figure that was reported in the Nature paper. What Justin and the rest of us, what we did for this data analysis was we just sort of binned things down by distance over the course of the encounter. And what we saw was that the off-radial flow, so the transverse speed, co-rotational part going around the sun, it actually got up to like 30, 40 kilometers per second as we came into the perihelion, which is more than 10 times faster than what we would have expected to see even in our wildest dreams. These observations, I will say, were made only with that SPC instrument, so the SAO instrument that we built, the one that's peeking off the heat shield, because we're not going sideways fast enough to measure the solar wind yet at this point in the mission with those other 2 detectors. So we don't have that corroboration. And that's pretty important because, of course, we would like very much to corroborate such a provocative measurement. This would have some pretty crazy implications. One would be that the Alphane point is actually more than twice as far out than we thought, and that the sun would be magnetically connected and torquing the solar wind out to a terrific distance. And the other implication of that, if you put that back into that back of the envelope argument about the spin down time for the sun, it would actually be only about 1 billion years. It would be 5 to 10 times faster than we ever thought. So that's quite provocative and also maybe a little alarming. That made us pretty concerned about whether we'd gotten something wrong. So the first thing we asked ourselves is, well, is it possible that the Alphane point was much higher than we expected, even if only nearby, i.e. were we about to cross the Alphane point? But the answer to that is no, and we measured that with pretty high confidence. We crossed a number of different streams that were fairly self-similar over the course of those encounters, and we mapped how the speed and how the alphanicity was changing over the course of those streams. Here I'm showing in the frame of reference that's rotating with the sun. This is what the solar probe orbit looked like for the first encounter. And this is an example of one of the streams here in green that we measured several times, that we crossed several times, and we were able to get a really good scaling. And it all holds together that when we measure the speed of the stream and we measure the strength of the magnetic field to try to get the Alphane number for the stream, it was about 15 our sun. And we repeated this exercise with several streams and projected similarly. And I'll also add that in later orbits, we've also skimmed the critical point. We've actually now made some measurements where the speed was almost equal to the local Alphane wave speed. And again, this all ends up happening, in the 15-ish our sun range. So that's not it. Next question we asked is, how representative were these observations? And the answer is not very. Both of these two encounters actually visited a very similar area of the sun. On the right here, what I'm showing is I'm showing magnetic maps of the sun that were accumulated over the course of the month around the first and the second perihelia. The colors represent where the solar sources would be for the solar wind, where the different lines of magnetic latitude were. And the red curve is the center line. So that's what we call the heliospheric current sheet. That's where that's the boundary between what we say is stuff that's coming from the northern magnetic hemisphere of the sun and the southern magnetic hemisphere of the sun. That's the dividing line between the solar wind that comes from the top and the solar wind that comes from the bottom. And what we saw is that in these two encounters, we are really skimming that boundary, and that's a crazy separator. That's a separatrix layer where there's a great deal of velocity shear and there's a great deal of magnetic field shear. So there's a lot that's going on at that point. And to make matters worse, from the observations, it looks like there was kind of a big wrinkle in that boundary right about where we were coming in. So we've seen structures like the heliospheric current sheet. We know about the heliospheric current sheet. We cross it all the time out here at Earth. Sometimes when it hits the Earth, it actually is associated with geomagnetic storms. And it's not at all unusual to have 40 kilometer per second flow in the vicinity of that. So that's one path to reconciliation with these observations. There were some other good suggestions that were also made. Ravi et al., a French colleague, suggested that there could actually also be a lot of other momentum that's carried in parts of the velocity distribution function that we weren't measuring yet. So if the particles are carrying a big parallel temperature component or a big heat flux, that could actually compensate part of the tangential speed that we were measuring, part of the tangential momentum that we were measuring. Ying Liu, who was my office mate at MIT, funny enough, he made the observation that if you were to account for the alpha particles and other heavier ions that weren't being measured by the suite at that time, they would also likely be carrying opposite angular momentum, and that might compensate a bit. And then Adam Finley also published a paper together with us showing that if you projected out over the course of the entire first and second orbits, the different tangential velocities that were measured, and you re-normalize that, integrated it by longitude, you'd find that there's really no contradiction. You get something that's much closer to classical expectations. And that what we're looking at right here is basically sampling bias. This just happens to be all of the data that we have from that close in at that point. And then finally, it's of course very much worth asking, and we ask this question of ourselves all the time, are the measurements correct? And the answer is we think so, and we've got some corroboration for that. One corroboration, which we're going to return to later, is that the solar wind was lousy with Alphane waves. And Alphane waves have a very particular property, which is that the magnetic field variations and the velocity field variations look exactly the same. They're transverse fluctuations of the MHD plasma. If you look at this middle panel of this time series here that I'm showing, you'll get an idea. One of those two curves, the red or the blue, is the velocity that's being measured by one instrument, and then the sweep instrument. And then blue is being measured by the fields instrument. And I think it's red and blue. I actually can't recall, and there's not much point in recalling because they're almost exactly the same. That's the point. These alphanic fluctuations are showing us that we're measuring the off-radial components of the speed very, very, very well. We have this completely physics-based independent corroboration. We also did commissioning slews, and things came out about as expected for the angular response of the instrument. But there has been some drama with the SPC sensor starting in encounter 4. And that is an important thing to keep in mind because it hasn't been entirely consistent. The way that we would like to, ultimately be absolutely sure about this is to compare it with the SPAN instrument, which is that other set of detectors that are on the spacecraft bus. But the SPAN field of view wasn't designed for that phase of the mission. It's designed for the later phase of the mission when we're doing those really deep dives into the corona. This is a cutaway of what our detector looks like. And all the magic happens at this red area. That's our segmented I'm sorry, it's not a photodetector, but it looks like a photodiode, right? That's our segmented detector, and that's where the direction finding happens, is from differencing incoming particle flow, which projects a spot down here as it comes into this cup, from differencing the amount of flux that's on those different quadrants. And in encounter 4, we started seeing crosstalk between these different segments. And worse still, we started seeing that crosstalk change. We have housekeeping diagnostics that tell us about that crosstalk. And we are now monitoring them very, very, very closely in order to take corrective measures. This crosstalk effect is thought to be related to a contaminating incident that occurred in ground testing. And it's kind of a sad story, but the instrument was in thermal vac at Goddard, and there was a mishap with a heating filament in the thermal vac oven, the brass heating filament. And we have confirmed that there was molten conducting material from that heating filament that was deposited into the instrument. And we went ahead because the best case scenario is that as that gets baked out in the sun, it'll sublimate off over the course of the mission. Worst case scenario, we could have some incidents like this where we'll lose a little bit of our direction finding or have to correct for it, as we're saying we're doing now. So from our 7th encounter out, we've developed a really, really good way to calibrate around this. And that's what I'm about to show you, because we're now on going into encounter 10. So in these plots, I'm showing those same plots from the Nature paper. We've got the transverse speed on the y-axis, and we've got the radial distance on the x-axis. And with blue bars, I'm showing binned down, whiskers of the SPC measurements. And you'll notice that as we get closer, for a lot of encounter 7 in particular, we're not making that measurement anymore. That's because the solar wind goes more and more out of the SPC field of view the closer we get in, of course. And then the red bars are the complementary instrument, the SPAN detectors. And there's no contradiction that these, by the way, blue measurements and red measurements don't match. They're complementary fields of view. So, if we bin down the results from one and we bin down the results from the other, we should be getting different answers. But the point is that the set of measurements taken together are going to show us the trend and are going to show us what kind of co-rotational velocity we're dealing with. And taking the two together, what we see is that actually there was in encounter 7, maybe even a little bit of extra flow going the other way, if anything. And there's a great deal of variation. There's a great deal of structure going in, just like there was in the previous result. I'm going to put the points from the Nature paper on there on top for context. And what you can see is that the structure with distance that we're seeing in the two instruments is more than enough to explain the fact that in encounter 1 and encounter 2, we happened to have this interesting co-rotational speed. It's also interesting to note that we crossed a pretty dramatic structure near perihelion of encounter 8, and we're studying that even now. It's probably also another case of a heliospheric current sheet crossing that has some really interesting structure, not likely representative of the heliosphere as a whole or the mass loss of the sun. So having put this all in context, the important things to take away here are that there's there's structure and there's spatial variation of tens of kilometers per second all over the place. And that secular increase in the original Nature paper is not something that we observed in subsequent encounters. We're going to look into that other, this interesting co-rotational feature here in the future as we're studying the heliospheric current sheet. But the main takeaway is that what we've seen so far is not representative. And I think Adam Finley is the guy who wins the competition for explaining those early observations. Now, in the last part of this talk, I'm going to talk about magnetic switchbacks. So this is the other major observation from the Nature paper was, like I said, we have these great big Alphane waves. We have these big changes in the velocity field and the magnetic field that go together, right? So another way of saying that is that the inner heliosphere appears to be just full of these compact plasma jets that are Alphanic, okay? They're transverse waves. We even see that the magnetic field folds all the way back on itself. You can see the magnetic polarity would be here on the y-axis of this middle panel, and then the transverse part right here. So anytime you see the blue curve go from one side of 0 to the other on this transverse part, you're seeing the magnetic field switch all the way back to point back at the sun. So these are S-shaped, really steep folds that are whipping out along the magnetic field. They pass by in timescales of minutes or less. If you were to average this all out, you would say that the average rate is a few per hour. But the fact of the matter is that these are patchy. The thing that determines the probability of seeing one is whether you saw one just now, right? You're more likely to see one if you just saw one. They clump together. Okay, so what's new about this? This is something that had been seen before, but we saw kinks like this in the fast solar wind and very rarely out at 1 AU, out near Earth, or in other missions further out like Voyager, okay? The new thing with Parker Solar Probe is that we started seeing them everywhere, and not just in the fast solar wind, but in the slow solar wind too. And that's very provocative, of course, because as you'll recall, one of the charter purposes of Parker Solar Probe is to figure out what the slow solar wind is. So this is telling us that the slow solar wind, as we get in closer to the sun, looks a lot more like the fast solar wind. Now, some follow-on papers that were studying the statistics of these things were able to show that the occurrence rate, once you get inside about half of an AU, is actually pretty constant, at least over the distances that Parker Solar Probe has probed. So from about 0.1 to about 0.5 AU, there wasn't a statistically significant correlation between the distance from the sun and the occurrence rate of these types of structures. They get bigger as you move out, of course. The filling factor grows with distance, and that's just because they're in the expanding solar wind. There was, associated with the fast solar wind observations, there was a theory put forth some time ago that this could just be warping of the magnetic field by flow shears. And having gotten to study the shapes of these things in great detail, it's pretty clearly not the case. If you had a magnetic field that was just warped by a sheared flow impinging on it, then you would see a certain profile where the extremes in the flow would be at the stationary points in the magnetic field, and instead we actually see that the extremes in the flow match up with the extremes in the kink. Another provocative observation that was made just this last year is that the scales of these patches that we see these types of jets occurring in have a characteristic scale. It wasn't obvious at first because they don't have a characteristic time scale. They don't have a scale that's characteristic of some plasma process. They have a characteristic scale in longitude, so in solar longitude. And what Nace Fargette and her co-authors, which include the team here at SAO were able to show is that if you model the expansion of the magnetic field away from the supergranular layer at the base of the corona, there's a very good agreement between the scale of the projection of those supergranules and the scale that we see for these patches of switchbacks. And Nace hypothesized that the patches that we see in the solar wind time series might just correspond directly to supergranular clusters, might actually just correspond one-to-one with supergranules. Marco Velli at UCLA, he furthered this observation, although I think that he actually technically got it published first, by looking at the turbulence. So the turbulence scales in the magnetic field in the solar wind in these switchback patches. And he made a really interesting and provocative observation, which is very circumstantial and a little tenuous, but it's worth making nonetheless, which is that when you look at the power spectra of these fluctuations according to the longitude, as opposed to in time, the cascade that you get out looks a lot like, a classical turbulent cascade where you put the energy in on one side and you see a power law cascade on the other side. And the break point between that energy input scale and that cascade is, wouldn't you know it, right around 2 degrees, which is the scale of the supergranules. So that also supports the work that Nace Farget published, and it seems to be a very it gives us something that we really need to keep our eye on going forward. Okay, now there was a whole special issue that was organized around this theme of switchbacks, where the leaders of the project solicited every theory. No theory would be too wacky about how you could create this type of magnetic structure and launch it into the solar wind. And we got a whole bunch of different classes of theories. And the idea was to come up with, what kind of predictions, as Parker Solar Probe gets closer and closer, are going to be testable. And we came up with a bunch of different types of theories. One is that you can get kinks in the magnetic field at places where magnetic field lines reconnect, particularly between a loop and like an open field, like around a coronal hole. Another is that the structure itself of a reconnected structure would contain kinks, would contain twisted fields, and then as those grow and expand, they would naturally drive this type of kinked structure. Another is that this would just be a natural shape for expanding ripples of plasma, so small scale fluctuations that you put into the plasma as the solar wind expands. Another is that it could be a particular kind of turbulence that you would drive at shear layers, so interfaces between places where there's slower wind and there's faster wind, like Kelvin-Helmholtz vortices. And then finally, there's this idea that actually at the boundaries between the slow wind, again, whatever it is, right, and the fast wind, you would have magnetic strapping from one type of stream to the next, and that magnetic strapping would create these kinks. So I'm going to show here, these are just glamour shots. I don't intend to explain them in detail because it would be out of my depth to do so, and it'd be sort of beyond the scope of this type of presentation. What I want to convey to you is that these authors rose to the challenge and came up with theories that would predict different frequencies of magnetic switchbacks with distance. Okay, and the two general ways, of course, that you could do that is you could invent switchbacks back at the sun, and then they could just be dissipative structures as they expand outward into the solar wind. So on the one hand, we have these impulsive types of mechanisms where you launch something on the sun, And then what we would expect to see with models like that is that the frequency with which we observe the switchbacks would go down with distance. And so one is that idea of, magnetic reconnections between closed fields, that the coronal loops, and streamer. Streamer is just a fancy way to say a corridor of open magnetic field. And then another one is that idea that if you had a closed magnetic loop or something like that with some torque, with some twist in it, then as that expanded and relaxed, you would get these types of signatures. So these are coming from the sun. These are coming from low down. And this is just a money figure from Jim Drake's paper, which I'm not going to get into, that's showing his simulation where they launch one of these flux ropes and it goes up into a corridor between a closed magnetic field and an open magnetic field. And then lo and behold, in time, it gives you the type of profile that you see with Parker Solar Probe. And then there's another class of theories here, which is that this is an evolutionary process, right? Where you have wave input at the base that's coming from the sun, and then at some sort of intermediate stage as they're coming out, because of wave interactions, as a natural consequence, you happen to get these switchback type structures. And that's not as contrived as it might sound. We know, for example, that in the solar wind, magnetic fields, they like to, or sheared magnetic fields, they like to collapse into current sheets. They like to form these very steep structures, and that happens very naturally as a consequence of the way that turbulent fluctuations evolve in the solar wind. And you get what some people like to call intermittency. You get very sharp structures as the wave field relaxes. So these are some authors that did some simulations of turbulent expansion, where they show that you could get these types of features just from having alphanic like inputs at the base of an expanding box model. And then finally, that field shear idea, the idea that you would have roll up vortices, at the Kelvin-Helmholtz layers between faster and slower solar wind, and that those would steepen. So this is another sort of turbulence theory, but it's the turbulence that's seeded by Kelvin-Helmholtz instabilities. And there was some demonstration that you could get this type of structure by Ruffalo et al. In 2020 doing that. And then that had a particularly interesting predictor there, because according to the Kelvin-Helmholtz instability theory, you would have a sort of preferred distance. You would have a preferred set of distances that are just beyond the Alphane point, where you would see a maximum in the occurrence rate of switchbacks, and then as you got further down, they would switch off. And then again, this idea of having strapping fields that go across different types of solar wind, and I don't have a good illustration for you of that. But that's another theory where we would see a local maximum in the occurrence rate of magnetic switchbacks down a bit above the Alphane point before seeing it go down when we pass it. So going forward now, here's a summary of what I've just told you about these issues of one, the rotational flow of the solar wind around the sun, and what we've learned, what we have learned from the reinterpretation of the data and from getting more data since that initial results paper. One, of course, is that the sun is probably not spinning down 10 times faster than we thought, as common sense suggests, and as we expected, and that the apparently large co-rotation that we reported in that Nature paper were probably sampling bias and having a lot to do with the heliospheric current sheet. And then with regard to magnetic switchbacks, again, these were features that were previously already seen in the fast solar wind, but now we're seeing in the slow wind. We're learning something new about the target state of solar wind that we want to study. And also, we have no idea at this point about how significant they are for the energetics of the solar wind, and whether these are leading us towards an energization and heating mechanism that we hadn't considered previously, or how these fit into one that we have. They've been circumstantially linked to solar supergranules, and we have really big zoo of different mechanisms that we can inspect going forward. Parker Solar Probe today is going to cross the Alphane point very soon, now-ish, actually. So stay tuned for that. I showed you data from Encounter 7 and 8, and I told you we're about to go into Encounter 10. And the data, of course, from Encounter 9 are under embargo right now, and that's something to keep an eye out for in the near future. And we're going to be very interested in seeing whether the frequency of switchbacks is going down when we get into the subalphanic region. That's going to tell us a lot about what they are and what they mean for solar wind heating. And then on the subject of measuring angular momentum loss, of course, I think that the main thing we've learned is that making strong inferences about angular momentum loss is going to be very difficult even when we do cross. But we're going to build up a great deal of statistical information about the inner heliosphere going forward. And then Solar Probe tomorrow, I'll remind you, Parker Solar Probe is going to reach its final orbit on Christmas Eve in 2024. And that's going to be an exciting time in particular because, like I said, we're on the rising phase of the solar cycle. Things have been very, very quiet early in the mission, which is great because it's been relatively easy to figure out what types of structures Parker Solar Probe is flying through and to look at how simple the magnetic structure of the sun looked at the time. We've been able to develop some pretty good mappings and some pretty good models of what the state of the heliosphere was. That's going to get much more complicated going forward. The sun is about to get much, much more dynamic. And then, of course, we're also going to be able to study eruptions. We're going to see eruptions being born. And also, we're going to give those people from ESIS, the instrument that measures energetic particles, something to do. So that's the end of my talk. I'd love to take any questions that you might have. Or actually, I guess John's going to take your questions.
Great. Thanks, Mike. Yeah, if you have any questions, just raise your hand. I think I'll be able to see that. There's one from Charles Alcock.
Hi, so thanks for this very interesting talk. I've followed the drama of constructing the sweep instrument in the lab, so it's just wonderful to see the science coming out. I'm just wondering, how well characterized at greater distances is the angular momentum content of the solar wind? Like, can you measure the angular velocity at say an Earth radius or maybe a few tenths of an Earth radius? It's
a really tricky question, right? Because we don't have a Dyson sphere where we can measure it at all points, and that's what you would need to really do it right? So that same author who led the study that I mentioned, Adam Finley, he did a paper a couple of years ago where he tried to do that from 1 AU, and he tried to estimate what the solar angular momentum loss was. And that's using 25 years of data, averaging or integrating a great deal of data in order to try to measure a very, very small effect. And he's putting the error bars on the angular momentum loss rate of the sun at about unity, right? So, and I forget what the actual figure is. I could go look up what it is in dynes per, well, whatever. But the point is that we know it better than an order of magnitude, but we don't know it to tens of percent. Mm-hmm. And there have been a lot of other missions. I mean, Adam's not the only person who's worked on this. There have been other missions that have gone out of the plane of the solar ecliptic as well. And so they've tried to tack that by actually figuring out what the profile is as a function of the latitude. But there's a pretty good agreement between a pretty long list of different investigations into it at this point.
Okay, thank you.
And a question from Arjun Day and or Joan Najita.
Do I pick Wu?
They are together. So
oh, they're together.
I'm assuming that one of them will ask. Hello? Arjun or Joan? I don't seem to be muted.
Can you hear me now?
Yes.
Yeah, we hear you now.
Okay. All right, sorry about that. Here, Joan had a question.
Sorry for the technical difficulties, but thank you for the wonderful talk. I thought it was really interesting comparing the situation here with the talk with the colloquium last week, where we found that protoplanetary disks were maybe a lot simpler than we thought. They're not turbulent. They have these, simple flows that you can really measure in great detail. Here, the sun is so complex. Was the amount of complexity that you discovered, what people expected or more, and how does the field deal with all this complexity? Is it possible to make predictions, or are we really going to need a lot more observations? What's the perspective on that?
Yeah, man, that's a really great question. I think that the field is very well acquainted with the complexity, and I mean, how could we not be? Because we can't predict the weather, right? We can't predict the solar wind. There's a whole office at NOAA, and then there's a great many labs around the world that are trying to, just when they see an eruption at the sun, trying to figure out exactly when it's going to reach the Earth, and they can't do it. It takes 2 or 3 days for it to get there, and they get an error bar of like 12 hours, right? And even when there isn't an eruption, just watching the tides, so to speak, just watching the same streams come around again and again, you would do better to just predict that the solar wind at the Earth is going to be the same as it was one rotation ago, and be done with it, which is kind of like, the almanac approach of saying that the weather today is going to be the same as this day last year. Then to use a physics model, then to use something where you actually take the magnetic, the remote observations of the sun and try to say something about what's going to happen in the solar wind. So everybody's very well acquainted with the complexity, I would say, and not at all comfortable with it. I mean, but this is the enterprise, looking for simplifying. We're looking for simplifying features that help give us some insight. And one of the real big merits of Parker Solar Probe is the expectation that we can go and we can actually fly through pristine solar wind streams. Out at 1AU, there's so much stochasticity. All of these streams that we see remotely, out at 1AU, they're all mixed up, and we know that they're all mixed up, and we know that we can't expect to do better. But if you can go to the point where where they're just separated by skinny shear layers, where they're separated by channels, and you can visit the different the sections that we know are there from looking at the sun remotely, we're hoping that we can make a lot more order of things. I'm not sure if that answered your question or if it was just a huge diversion.
Thank you.
Can I, since we have the microphone on here, can I ask another question? This was sort of the picture that you have up here on the screen shows all the stars moving to the right, but then there's an object that comes in on the left that's rather bright, sort of halfway through, right there. What is that?
Yeah, is that Comet Lovejoy? I'm trying to remember when actually this one is from. I don't think it's Lovejoy.
No, Lovejoy came in from a different angle.
Yeah.
It's probably a planet.
Yeah, it's this thing here.
Oh, hey, cool. How do you do that? Oh, thanks, John. It is probably a planet. You're right. We might be seeing a comet that far out, but that would be very lucky.
Oh, thanks.
I couldn't tell you which planet it is.
So I had a question. As you know, Yami is working on these composition anomalies seen at 1AU, and they have typical timescales of a few hours, which if you de-expand that back to 10 solar radii would be, minutes, kind of on the order of the switchback timescale you talked about.
Right. Yeah. Maybe 10-ish minutes.
Right. So if there is some connection between those two, would that indicate that the reconnection type theories are more likely, flux ropes and things like that?
I think that it would. I do. And I think that well, there's some interesting stories about the instrumenting of Parker Solar Probe, because as you know, John, the composition measurements that it can make are not at strength. There's another mission, Solar Orbiter, which again, you know about, but maybe the rest of the audience doesn't. There's another mission, Solar Orbiter, which isn't going nearly as close as Parker Solar Probe, but it is making interheliospheric measurements, and there are a great many interesting conjunctions between the two. And it's instrumented with some really great composition instrumentation. So I think we're hoping that we're going to be able to look at conjunctions between Parker Solar Probe and Solar Orbiter, and suss out when we're crossing the same feature, using other information, of course, from Solar Probe, like just magnetic structure and so forth, and then make the composition measurements from Solar Orbiter, and then we'll be able to get to the bottom of problems like that. Solar Probe does have some composition measurements. Of course, it measures the helium composition. It doesn't measure the zoo of charge states that some other spacecraft can.
Great. Let's see, we are past 5, so one last question from Ramesh.
Yeah, I was hoping you'll tell us something about coronal heating. Some new clues that you've got from Parker Solar Probe. So it's clear that you're not going to tell us, you're not going to let the cat out of the bag. But in the context of your talk, these switchbacks, do they have enough energy locked up in them, whatever extra free energy? Is that enough to do a substantial part of the coronal heating, or are they really energetically not so important?
I mean, I think we're going to have to get closer before we'll be able to answer that definitively. But I think right now the answer is that they don't carry nearly enough energy to suggest that. So we were looking at this. We're looking at this earlier. The filling factor is something like it's something like 6% of the solar wind, and the, well, I don't know if that gives you an idea of scale or not. The point is that they're not nearly pervasive enough that we would expect that. But are we going to see totally different phenomenology when we get down below the Alphane point? I don't know.
Yeah, thanks.
Okay, thank you everybody for joining us. Thank you, Mike. That was a great talk. And we'll see you at next week's Colloquium.
Thanks.